Good morning students. Class 12th, chapter number 6, applications of derivative, lecture number 8. So in today's lecture we are going to start with a new concept of maxima and minima. The topic is really important from board examination point of view as well, because every year you are going to get a 6-mark question based on the same concept of maxima and minima. So you need to really understand the topic well. So before this we have already gone through basics. Now let us start with the new concept, maximum and minimum values of a function in its domain. So in the previous chapter we have learnt about various applications of differentiation. In this chapter we will use differentiation to find the maximum and minimum values of differentiable functions in their domain. In the end of the chapter we will discuss applications of maxima and minima in solving some applied problems. Now to understand first maximum, we will assume a real function f of x, and suppose it is defined in the interval a comma b. Function f of x is defined on this interval in the closed intervals a and b, where a and b are included. Then f of x is said to have the maximum value in this interval if there exists a point c. In this interval only, c will belong to this interval a comma b only, which is given, on which the function is defined, such that f of x is less than equal to f of c for all the values of x that lies between these two values. What do we mean by it? There is a function which is f of x and it is defined on the interval a comma b in the closed intervals, right? Then there will exist a point c in this interval only, at which f of x means you put any values between this interval a and b, all the values you put here, at that value the function fx is going to be less than or equal to f of c. That means f of c will always be greater than f of x or equal to f of x. Point c is called as point of maximum value of f in the interval a comma b. So f of c will be what? The maximum value, right? And what will be point c? Point of maxima or point of maximum value. Clear? Now the statement that I have just explained you, I'll be explaining through a graph paper. We'll just draw a diagram on the graph paper and we will learn how the statement works, and it will give you a more clear idea. Now as you can see, I have drawn a graph on which I have drawn the function f, graph of the function f of x. I have drawn the graph of the function f of x. When we see it carefully, see it is defined between the intervals a and b. So in between a and b there exists a value c at which the value of the function is maximum, which is f of c, right? And f of c is the maximum value, point c is the point of maxima. Clear? This is how we calculate, and this is what I meant by the statement. So I am again repeating it. What is maximum? How do we find the maximum of a function? If a function is there which is real valued function and it is defined on this interval ab, then there will exist a point c in the interval a comma b, such that you may write it or mention it that such that f of x will always be less than or equal to f of c. Now you see, you put any values between the interval, we see all the values are less than, whether it is onto the left side or onto the right side of the point c, they are less than f of c. F of c is the maximum value of this graph drawn or the curve drawn. Clear? So this point is known as point of maximum, or the value is known as maximum value of the function. Similarly, we can now understand minimum. Now as you can have a look on the curve y equals f of x, it is also defined between the interval a and b, and at point c we see the minimum value of the function. F of c is known as the minimum value or minimum value of the function, and point c is known as the point of minimum. This is how we calculate. Now we can understand maxima and minima with an example. Before that, in maximum I wrote the function value will be less than f of c, but in case of minimum what we will have? We have to reverse it. We will write f of x will be greater than or equal to f of c in case of minimum, right? This is the condition for maximum. So for minimum, the values of the function at the point x is lying between a and b, at all these points the function value will be greater than the value of the function at point C. Hence point C is the point of minimum. Suppose now we take an example for maxima. The function given is f of x equals minus of x minus 1 whole square plus 10, where x belongs to capital R. Now if we go with the domain of the function, we know we can put any real number. For all the real number, all the different real numbers, we are going to get different values of the function. So we know that the domain is from minus infinity to infinity, right? We can write it like this in the open intervals. Now talking about the maximum value of the function, just see carefully, minus of x minus 1 whole square. Because it is a negative number, the square value is always going to be positive, but the negative sign in front of it is making it negative, which is less than or equal to 0. Clear? Now to make this function I have to add 10 on both the sides. So adding 10 on both the sides, we get here this side our function and this side we get as 10. This complete is what? F of x. So it is coming less than equal to 10. That means either it will be 10 or less than 10. So the maximum value that this function can reach up to is 10. Hence we know 10 will come at x equals 1. Right? When we put x as equal to 1, this will become 0 and f of x will come out to be 10. So the maximum value is 10 of the function f of x, defined as minus of x minus 1 whole square plus 10, and 1 will be called as the point of maximum. Clear? Similarly, let us take one example for minimum. So let us consider f of x as equal to x square plus 5. Now to calculate its value, just to see, x square will always be greater than or equal to 0. Adding 5 on both the sides, we get 5, greater than or equal to 5. So our function f of x is coming as greater than or equal to 5. That means the minimum value is 5. It can be 5 or more than 5. So we write that the minimum value will be 5. And 5 will come at what? When x is equal to 0. So 0 is the point of minimum. Clear? This is what actually meant by those. Now we are going to discuss another topic, local maxima and minima. First of all, we'll start with the local maximum. A function f of x is said to attain a local maximum at point x equals a if there exists in the neighborhood, we can consider the neighborhood as a plus h or a minus h, right? So writing a minus h first, comma a plus h, such that our function value f of x is less than f of a. That means at a we have the greatest value, and where x belongs to this interval, this one, right? So what do we mean by it? That in the neighborhood of a, if we are checking for the values, we are putting values less than, just a very small value less than a and a small value greater than a. When we put in the function, it is always going to be less than f of a. That means f of a we have the maximum value. So we call it as f of a, the local maximum value at point x equal to a. So a will be the point of local maxima. Similarly, for local minima, we can write it at in the reverse manner. Local minimum I can write. So if f of x is a function and suppose at x equals to a, this point will be known as point of local minima if there exists in the neighborhood. Neighborhood is this only, a minus h and a plus h. So such that f of x is greater than f of a. That means you put values in the neighborhood of this point, you are going to get all the values greater than this point. That means this point is the point of local minimum. This also can be well understood through a graph. Let us draw that. Now in this graph paper, we observe that the x coordinates of the point A, C, E are the points of local maximum. A, C and E, in their neighborhood they are highest, right? And the values at this point, that is their y coordinates, are the local maximum values of function. If we look at the point B and D, they are the point of local minima because they are having less value other than all the values in the neighborhood. Otherwise, for the complete graph, if we see, ICC is the maximum value. Correct. But if we talk of local maxima and minima, in their neighborhood we are going to check. So A, C and E, this point, these three are local maximum. The values are local maximum and the points are local maxima. Now B and D are the points of local minimum. Clear? This is what we meant when we discussed A plus H and A minus H. Means suppose this point is A and just close to this, suppose A minus H and A plus H. In this portion we have checked. Like this we are going to check for local maxima and minima. Let us now discuss first derivative test. Let f be a differentiable function defined in the interval. Let the interval be named as I. Okay, this is our interval and f is our function. So this is our function. So what I am saying, let f be a function, a real valued function which is a differentiable also defined on the interval I, and let a belongs to that interval I. A is a number that is lying between the interval only. Now then the first point, x equal to A is a point of local maximum if first point f dash A is equal to 0. Second, these are the two compulsory conditions, f dash A equals 0 and f dash x, that means the first order derivative, the tangent, changes its sign from positive to negative. Okay, why this is being said? Just to see here, if I draw a rough graph for you people like this. So just to see here, let this be x, let this be y, this is our origin. Okay, now suppose this is the curve. Okay, and we are checking at this point. This is our point A. Now if I check f dash A equal to 0, I will definitely get some points by putting the first order derivative as equal to 0. We get some points. Those points are known as critical points. We can name them as C1, C2, C3. Those are also known as your stationary points. Clear? So now we are going to check f dash x. This is what f dash x means, the tangent. At this point we can draw a unique tangent. So just to see at point A, suppose A is the critical point at which our derivative is getting 0. So you are going to just check in its neighborhood, just a value below here and a value after here, right? A value less than A and a value greater than A. So see, the f dash x is increasing here. So it is positive here and going negative, going downwards. So from upside it is going down. That means from positive it is becoming negative. Whenever this happens, this point is known as the point of local maximum. Clear? This is how we are going to check for it. Also, it will be known as a point of local minimum if f dash x changes its sign from negative to positive. Now if we check at this point, just see, it was decreasing, that means it is negative, and then it has start increasing. So from negative to positive if it is getting, then it will be a point of local minimum, otherwise a local maximum. Clear? The third point, if f dash x is not changing its point, right, it remains the same, then we call this point A as the point of inflection, we say it. We call it as the point of inflection, that the sign is not changing. If it is positive, it is remaining as positive, it stays the same. So at this point A is known as point of inflection. Clear? So three things are clear: local maximum, local minimum and point of inflection. This is our first order derivative test. So I am just explaining using the algorithm how you are going to actually proceed for questions. Just to see, first of all, the function will be given to you. You have to obtain dy by dx. Correct? So you will get f dash x. Now when you find dy by dx, you are going to put it as equal to 0. Clear? From here you will get critical points C1, C2 or C3 up to so on. You can get any number of critical points. Now critical points are also known as stationary point. Do keep that in mind. Now on this particular values C1, C2, C3, you are going to check f dash x. Just put a value smaller than C1 and greater than C1. Put in this and check if it is going from positive to negative, it will be a point of maximum, and from negative to positive, it is a point of minimum. Clear? So this we are going to check, and if it does not change the sign at all, then the point is a point of inflection. This is how we are going to solve the questions. So let us just understand one question based on this only. Suppose the question is given as f of x equals x cube minus 6x square plus 9x minus 8. Suppose this is a function and they are asking you find all the points of local maxima and minima for this function. So first of all, I told you are going to find out the differentiation of it. When you differentiate it, okay, what will you get? 3x square minus 12x plus 9. Clear? We get this. We can take 3 common. X square minus 4x plus 3. This is what we are getting now. This is what we are getting now, x square minus 4x plus 3 inside the bracket. Now we will put it as equal to 0. So putting 3x square minus 4x plus 3 as equal to 0, just to see we will obtain the factors. You know all splitting the middle term method, how we can write it as x square minus 3x minus x plus 3 equals 0. So just to see x will be common first time in the first two terms, you get x minus 3 plus, then what to take common from here? Minus 1, right? If we take minus 1 common, then we will get x minus 3 inside the bracket again. So we have two factors, x minus 1 and x minus 3, and 3 was there already. So using the zero product property, we have x equal to 1 and x equal to 3. We have two values of it. Now just to see if I plot them on number line, 1, 3, here we have minus infinity and here we have infinity. First thing, you can just check whether the function is increasing or decreasing in these intervals, as we have already done in one of the exercise. Suppose it is like this, plus, minus and plus, that means increasing, decreasing and increasing. So what you can do is, you can just see from 1, it is going from positive to negative. If we check through 1, from left to right, it is becoming positive to negative. So from positive to negative, it is becoming like this, right? From positive it is going down, that means negative. That means this point will be a point of local maximum. And from 3, if we check, what is happening? Negative to positive, that means decreasing to increasing. That means this point 3 will be a point of, this point will be 1 then, right? So this point 3 will be the point of local minimum. One way is to do this. Another way is that we have discussed using the first order derivative test is, just to see at 1 you are checking. Okay, first of all, what will be f of 1? F dash 1. Let us calculate. I will be just doing for 1. The rest you can check, second point can check in your notebooks. If we calculate f dash 1, we get 3. 1 minus 4 plus 3. Just to see, because this is a critical point, we are going to get the value as 0 here. Clear? So I am not solving it completely, just writing it directly. Now just to see, from a value which is very small than 1, let us take it as 0.8. Okay. So at f of 0.8, when we put in our differentiated function, just to see we are going to get a value which is greater than 0. I have just placed 0.8 in place of x, and then I tried to place 1.2 at the place of x. So the sign of f dash x is changing from positive to negative. It is coming less than 0 in the second time, it is becoming positive to negative. When it goes from positive to negative, as already shown in the graph paper, positive to negative means what? Positive to negative, that means going downward. The point is of local maxima. So here 1 is the point of local maxima. Similarly, you can check for 3. Clear? Now you notice one thing, doing the first derivative test has a lot of things to do and is time consuming, and every time to do this is not possible for us because it takes a lot of time. Then to avoid this, there comes a second derivative, we call it as second order derivative test or call it as higher order derivative test. Let us discuss that. That will make us calculate the point of local maxima and minima in a lesser time and more easily. Also, if you suppose I have got here 1 as the point of local maxima, then I am going to put 1 in this function and I will get the local maximum value. Clear? Similarly, if 3 comes to the point of local minima, I can get the point minimum value from f of x. Let us now discuss our higher order derivative test. So what we are going to do in this, first of all you will be given a function, you are going to differentiate it, you will find f dash x, then you are going to put your f dash x as equal to 0 to obtain the stationary or the critical points as c1 up to cn. Clear? Then you are going to find out second order derivative of x at point c1 or c2 or c3, whatever you want to check on. Clear? Now if your second order derivative is less than 0, clear, then suppose it came at x equal to c1, so I can just write it at f double dash c1, that means the second order derivative of this point is less than 0. Then we call this point c1 as the point of local maxima or local maximum. Clear? Otherwise, if it would have come as greater than 0, then C1 would have been called as point of local minimum. Clear? This is how we are going to check using second order derivatives test. So here we don't have to do much of the calculations. We just have to differentiate it twice, find out the critical points, put them in the second order derivative and check whether it is less than 0 or greater than 0. Do remember the conditions, do note them down in your notebooks. They are really helpful in solving your questions. Clear? Now we are going to discuss exercise question based on local maxima, minima, maximum and minimum that we have discussed, and the first order derivative and second order derivative test. So let us start our most important exercise, exercise 6.5. Let us start with question number 1. Question number 1, first part. Okay, the statement of the question is, find the maximum and minimum values if any of the following functions given by. The first function is f of x equals 2x minus 1 whole square plus 3. Now see carefully, 2x minus 1 whole square, because it's a square number, will always be positive or greater than equal to 0. Now adding 3 on both the sides, we get 2x minus 1 whole square plus 3 greater than equal to 3. So we see this function is always either equal to 3 or greater than 3. So the minimum value is 3. So we will write minimum value for this function is equal to 3. And maximum value we don't know up to which value it will go, like it can go to infinite. So we write no maximum value. Right? This is how we are going to solve question number 1. So there are 4 parts in question number 1. I have explained you one. You can go with other parts. So you can solve, I think, second and third part. Also fourth part. Let me give you a hint about second part. In the second part, it is given as 9x square plus 12x plus 2. So what you can do is, you can go with completing the square in this. Clear? And then can apply this concept to find out the maximum and minimum value. Clear? Let us go to the second question now. In question number 2, first part, the function given is f of x equals modulus of x plus 2 minus 1. Now we have to again find out maximum and minimum values if any for this function. We know modulus of x plus 2 is always going to be greater than or equal to 0. We will subtract 1 on both the sides. We get x plus 2 minus 1 greater than equal to minus 1. So you see here the function, this complete function, now this has become f of x, which is greater than equal to minus 1. So the minimum value of the function is minus 1 and other values are greater than minus 1. So we will write the minimum value is minus 1, and for maximum we will write no maximum value, because we don't know up to which value it will go up. So no maximum value. Clear? Let us discuss another question. Question number 2, third part, h of x, which is a function of x given as a sine of 2x plus 5. We know any angle of sine we have, the values lies from -1 to 1. Right? Now to make this function complete, we have to add 5 on all the sides. We will write -1 plus 5 less than sine of 2x plus 5 less than 1 plus 5. We get it as 4 less than, we can write it as now h of x as given in the question. So sine of 2x plus 5 is hx less than equal to 6. Now we see here that the function is equal to 4 or greater than 4 and less than 6 or equal to 6. So the minimum value that we can write for this function is 4 and maximum value is 6. So this is based on the first two concept, maximum and minimum, that we have learned. Clear? Here we're not using any derivative test or something. We don't have to tell the point of local maxima, minima or something. Clear? So similarly you can solve other questions as well. Now there comes question number 3. Here you can see question number 3. We have to find the local maxima and local minima if any of the following function. Find also the local maximum and local minimum values. We have to actually find the points also and the values also, as the case may be. Now first part, f of x equals x square. So first of all, the first step is to go with f dash x, find out the first order derivative, which is coming as 2. Now equating it to 0, we get x as equal to 0. Now find out from here second order derivative, f double dash x. Now it is coming as 2, which is greater than 0. Correct? So we can say the double derivative of the function, the second order derivative or higher order derivative, is greater than 0 in this case at x equals to 0. So when it comes greater than 0, I told you it will be a point of local minima. So here 0 is the point of local minima and f of 0, if we calculate, it is coming as 0. So local minimum value is 0. We can write local minimum value equals 0 and point of local minima is equal to local minima, or we can call it minimum, is equal to 0. Clear? Because x is coming as 0 and there is no maximum value. Clear? Now I am going to solve the second part to show you the difference. Just to see, if we solve the second part, g of x is given as x cube minus 3x. Let us first find out g dash x. What we get? 3x square minus 3. Correct? Now putting it as equal to 0, 3x square minus 3 equals 0. 3x square minus 1 equals 0 and we get x plus 1 and x minus 1 as equal to 0. So we get two values of x1 and x as minus 1. Okay. Now let us find out second order derivative. I am just writing it here, second order derivative value. So just differentiate it. We get 6x. This is our second order derivative. Now what is the procedure? I am going to repeat the algorithm again. First of all, find out first order derivative. Equate it to 0. It is going to give you values of x, which are actually known as your stationary points or critical points. Find out second order derivative test. Put those stationary point in the second order derivative and then you're going to check whether it is greater than or it is less than 0. Now if I check at 1, so second order derivative at 1, just to see here, you put 1, you are going to get 6, which is greater than 0. And when you get second order derivative at minus 1, you will get minus of 6. So which is less than 0. Now when second order derivative is greater than 0, here also it was greater than 0. So it was a point of local minimum. Correct? And here this will be a point of local maximum. So local minimum point is what? Here 1 and local maximum point is minus 1. Similarly, we can calculate local minimum value and local maximum value. How we are going to check that? We will calculate g of 1 and g of minus 1. Now we have already seen that 1 is the point of local minima. So we are going to get local minimum value. The function is x cube minus 3x. Putting the values in x cube minus 3x, just see you get 1 minus 3, which is minus 2, and when you put minus 1, so minus 1 minus and minus will become plus, so you get 2. So minus 2 will be the local minimum value and 2 will be the local maximum value. It depends on the point. If 1 is the point of local minima, then minus 2 will be the local minimum value, and local minimum and maximum value will not be calculated by placing 1 or minus 1 in the derivative part. We are going to place in the original function that is given in the question. Clear? So question number 3 has many parts. It has 8 parts. 2 of them are explained by me. The rest you can perform at home. So now for homework, what you are going to do from exercise 6.5, you will complete question 1, 2, 3 and try to do question number 4 also. Right? So there are 4 questions only. The reason is I want you to revise the summary of this or the theorems whichever are given based on this concept. Whatever diagrams are given, the graphs are given, the curves are given, do go through them carefully. Do these 4 questions, because after this the questions that we are going to do are only 6 markers and they are real time application based questions. So you're really going to enjoy them. They're really interesting and those are helpful for board exams. Every time you're going to get a 6-mark question from this. So for more videos like this, do subscribe the channel AdQuark and keep liking and sharing the videos.